Welcome to the A-level tutorial on kinematic variables. When we say kinematic, we mean when something is moving. Therefore, the variables that we're concerned with are going to be firstly, the distance, secondly, the speed, thirdly, the acceleration, and then lastly, as an aside, we have time. When writing equations, we need to be able to represent these variables very simply, and so we call distance the variable s, speed the variable v, acceleration the variable a, and time the variable t. Above are the kinematic variables as scalars, where scalars have only a magnitude or a size. For example, if I told you that a car is 10 meters away, then you know its magnitude, 10. But what you don't know is its exact position, because if I told you it's 10 meters away, you don't know in which direction to look. Therefore, to get that extra information, we can also define vector quantities for the kinematic variables. The equivalent for distance will be displacement. The equivalent for speed will be velocity. The vector acceleration is once again called acceleration, somewhat confusingly. And time is always scalar, so we'll ignore that. And then once again, we have symbols, and when working in vectors, we simply put a line over the top of the scalar variable, as such. There are other ways to denote vectors, however, in all of my tutorials, I shall be using this notation. So how do we relate these variables? So we can only really relate vector quantities to other vector quantities, and scalar quantities to other scalar quantities, with the exception of the scalar time, which can be used for both. So, if we denote relations to be below this point, let's work with our scalars first. Firstly, we can define the average speed. Instantaneous speed, which will just be v, will be found in later videos. We can denote the average speed to be equal delta s over delta t, where delta means change of. This means that when we do an example, we will say that delta s is equal to the final displacement minus the initial displacement. Don't worry about this now, wait until the example before you see this. Then secondly, we can denote the average acceleration, which will be delta v over delta t, or the change in speed over the change in time. We can do the same with vectors. We can say that the average velocity is equal to the change in displacement over the change in time, and that the average acceleration as a vector is equal to the change in velocity over time. Let's try and make sense of these equations. If we look at this equation here for the average speed, if we have a certain distance delta s and we have a certain time delta t, if the time was to increase, or we would take longer to travel a certain distance, then there will be a bigger value on the bottom, which means that our average speed would decrease, which makes sense. Our average speed would be lower if it took longer to get to a certain place. And then secondly, when considering our acceleration formula, we're considering a change in speed over a change in time. For the same change of speed, if our time took longer, then it means that we're accelerating slower, and therefore A actually decreases, which makes perfect sense. Lastly, let's talk about units. For distance and displacement, the units is meters, which we say as m. This makes sense because when we measure a distance, we might measure it with a ruler, and so it might be centimeters or millimeters, but they are some denomination of meters, which is m. That's simple. And then, let's say over here, we have time t, which has the unit seconds. When we measure time, we will say either an amount of minutes or amount of hours, and therefore we can relate all of those values to seconds. Let's move on to speed or velocity. As you can see, in either of the two velocity or speed formulas, we have a distance divided by a time, which means in all of the formulas we have meters divided by seconds, and this means that our units are meters per second. Lastly, our acceleration, or our acceleration vector, we now have a velocity, or a speed, divided by a time, which the units are meters per second divided by seconds. And so now we have two lots of seconds on the bottom, which gives us meters per second squared. You can see that you can do division with units as the same as you could do multiplication. This is called dimensional analysis. Let's look at a simulated example. At the top of the screen you can see a rover on the surface of the planet. This planet is the exoplanet TRAPPIST-1d, which is a recently discovered planet. This rover is going to travel forwards, and then we are going to try and calculate its average speed and average acceleration. The information given is that the distance travelled was 4.61 meters, the speed decreased in the hole by 0.05 meters per second, and that it took 5.83 seconds for these two things to happen. Firstly, let's work out the average speed. We know that this is equal to the change in distance over the change in time, which, if we sub in our values, is going to be 4.61 divided by 5.83. This will be equal to 0.79 meters per second. Secondly, let's work out the average acceleration, AAV. This is equal to the change in speed over the change in time. Now, when we sub in our values, we get this. When dividing such a small number by a fairly large number, this is going to be almost exactly 0. So therefore, I'm just going to write approximately 0 meters per second squared. Let's compare these two values to the graphs of speed and acceleration over time to see if this makes sense. Let's play the animation through. As you can see, for the speed time graph, the speed hovers roughly around the 0.8 meters per second value. It does spike above and below this, but on average it is roughly 0.8 meters per second, which means that this value here looks correct. You can see how the average speed is not completely accurate for every single time, but is a good indication of, on the whole, what happened. Secondly, for the acceleration time graph, you can see that it's a very messy graph and that the values range mostly between -1 and 1 meters per second squared. But as you can see, on the whole, the amount of positive and negative values roughly equal out, meaning that we have an acceleration on average of roughly 0 meters per second squared, as we predicted. Hopefully, these two graphs and these two values show that an average acceleration or speed is a good indication on the whole, but is not entirely accurate for specific parts of the graph. Instantaneous speed and acceleration will be a much better indicator for those types of tasks, which is something that will be covered in later videos. Let's have a go at a couple of mathematical examples. Firstly, a car travels a distance of 10 meters in 5 seconds. Find the average speed. We know that it travels a distance of 10 meters, so therefore the change in distance, delta s, is equal to 10 meters. Secondly, we know that the change in time, delta t, is equal to 5 seconds. We also know from earlier that the formula for average speed is equal to delta s over delta t, meaning when we sub our values in, we get 10 over 5, 10 divided by 5 is 2 meters per second. And you know it's meters per second because our distance, delta s, has units meters, and our time has the unit seconds. So we have meters per unit second. Let's move on to the second question. A car accelerates from 2 to 10 meters per second in 8 seconds, and we must find the average acceleration. Let's list down what we know. We know that the initial speed, vi, is going to be equal to 2 meters per second. We know that the final speed will be equal to 10 meters per second. And we know that the change in time is equal to 8 seconds. The formula for average acceleration is equal to the change in speed over the change in time. The change in speed can be rewritten as the final speed minus the initial speed, as discussed in the theory section for distance. Therefore, when we divide by the change in time, we will get our answer. Let's sub in the values we jotted down. V final is 10 minus V initial, which is 2, over the change in time, which is 8, which is equal to 8 over 8, which is equal to 1 meters per second squared. You know the units are meters per second squared because our speed has the units meters per second and our time has the unit seconds. And so therefore meters per second divided by second is meters per second squared. Let's move on to the next question. Now we're working with vectors. We can see that our car has a starting and a final displacement and a time 5 seconds, which are conveniently written down in the question. We shall jot down the one that isn't written as a formula, which is delta t is equal to 5 seconds. We additionally know that for vectors, our average velocity is equal to the change in displacement over the change in time. And this is going to be equal to the final displacement minus the initial displacement over the change in time. Subbing in the values that we have in our question, we know that this is 4x hat plus 5y hat with a bracket minus 2x hat plus 2y hat, all divided by our change in time 5. So for the x hat values, we have 4 minus 2, which is 2x hat. And then for the y values, we have 5 minus 2, which will be 3 y hat. and once again divided by 5. This means we have 2 over 5 x hat, which is 0.4, plus 3 over 5 y hat, which is 0.6. And as this is a speed, we have the units meters per second. We know that a car is first reversing at 2 meters per second, then after 10 seconds it's travelling forward at the same speed in exactly the opposite direction to the reversing. And we need to find the average acceleration vector. Let's start off by writing down our average acceleration vector, which is equal to the change in velocity over the change in time, which is also equal to the final velocity minus the initial velocity over the change in time. Therefore, to solve this question, we know that we need to find the final and initial velocities and the change in time. The change in time is easy in this question. It's told to be 10 seconds. But how about the initial and final velocities? Well, we've been told that at first a car is reversing at 2 meters per second, and that in the end it is travelling forward at the same speed in exactly the opposite direction. If the final and initial velocities are taking place in exactly the opposite directions, then it means they can be assumed to be travelling along one axis. So we're going to make up an axis, as we don't know if it's travelling in the x or the y or the z direction typically, and so we can just make up one. We're going to call it a hat. And so our car will be travelling either forwards or backwards along the a hat direction. For example, if we have the y axis and the x axis, our a axis could be in this direction, because that is the direction we've decided our car is moving, as we haven't been told any more information. The units for velocity will of course be meters per second, so we can write that down too. And then we've been told at first it's reversing at 2 meters per second, and then at the end it's travelling forward at the same speed, which is also 2 meters per second. Our final velocity, our car is travelling forward at 2 meters per second, so therefore we can write 2, and then initially our car is reversing at 2 meters per second, so we can say minus 2, like that. And therefore we've done all the hard work, and we can now work out the average acceleration, which is going to be, after subbing into this formula over here, the final velocity, which is 2 a hat, minus vi, which is minus 2 a hat, over the change in time, which is 10 seconds. 2 a hat minus 2 a hat is adding, and that becomes 4 a hat over 10, which is the same as 0.4 a hat meters per second squared. And so what does this mean? It means that our car has an acceleration of 0.4 meters per second squared in the positive a hat direction, where a hat is the direction of the car at the end when it's travelling forward. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.